So, as I said, I'm not going to spend too much time on myself. Fundamentally, the important parts are that my background is in kind of traditional AI. That's what I studied in university. Did a bunch of neural network stuff. Fundamentally focused on more graph search, pathfinding, because I want to get into games as an AI programmer. So I kind of focused on the locomotion, that kind of stuff. Within games, I primarily worked on, Hitman Absolution, a bunch of the Hitman games. Was also involved with AI on Far Cry when I was at Ubisoft. And then at Warner, we had a council project where I was sort of salvaging whatever AI systems were there. And then on Gotham Knights, I was involved from the start. Basically architected and built a lot of the foundational systems for all the AI stuff there. So that said, we got a lot of stuff to go through, so I'm going to go through some of the stuff relatively quick. If we want to talk about resources, outside of this for people that are interested in finding out how some things work in games, general AI concepts, those sort of things, these are some of the better references I have. For games specifically, the Game AI Pro books have quite a lot of good information. If you want to go back in time, there's also the thing they're called the Game AI Wisdom books. GDT talks are kind of useful, but they sort of assume a bit of prior knowledge a lot of the time because they don't go too much in depth due to the time limits. When it comes to general AI, I highly recommend that book, Artificial Intelligence: A Modern Approach. That's sort of where I started, and I still think it's one of the kind of best books in the field as a good introductory text. When it comes to game AI, there's not that many books out there anymore. These are the two main ones that are out there. They are very introductory at best. I have opinions about the Millington Funge book. I still think it's worth reading. There's a lot of good information in there, but I definitely wouldn't use it as a basis for building anything. There's a lot of naivety in some of the suggestions and stuff covered in there. So just take that with a grain of salt. But as an overview of a lot of the kind of different terminology and stuff in the industry, it's kind of a maybe a good kind of primer, an intro. So let's talk about game AI. Now, this is where maybe things get a little controversial to some degree. Game AI is not so much AI. As much as everybody wants to call it AI, and game AI programmers will often say, consider themselves AI programmers, it's not really what we're doing. And I'm talking about gameplay, sort of in-game stuff, moment-to-moment AI. I'm not talking about analytics, content creation, like stats generation, a lot of that kind of stuff where we do use a lot more actual traditional AI approaches, machine learning, classifiers, a lot of that stuff. But within the concept of runtime game AI, there's not much there. And the goals are very different. The goals are to facilitate gameplay. We are just simply trying to make the game interesting for the player. We are trying to provide a level of interactivity to the player. The player does an action, the in-game characters need to react to that action. And that's the foundational kind of core premise for game AI. And so we're not trying to solve a realism problem. We're not trying to build an intelligence. We're basically trying to create a toy. And that's one of the big things that a lot of people need to understand, and they need to come into it with that approach, is that we are building a toy. If we look at all the games, even the Sims, they are not FIFA or the kind of hardcore racing game and stuff. They are still kind of gamey in a lot of ways because they have to be due to the input constraints, due to the medium, those sort of things. They are still gamified in a lot of ways. And if we start to look at the actual games, there's little to no realistic reactions to things. We have to artificially delay, reactions, have to have non-realistic responses to the player's abilities and those kind of things because we want to have a specific gameplay loop. We want to have a specific reaction, those sort of things. So The other key thing that is really important is that a lot of those responses to the player, they have to be reproducible. They have to be learnable. They have to be telegraphed, right? As the player plays the game, they want to learn it. They want to know if I do action X, the response from the game will be Y, right? They don't want a random thing where I do the same action, I get different responses every time, and now I don't understand what's going on, and the game feels broken or janky or something, right? So those are very key motivational aspects for what we're trying to do. Additionally, like a lot of people kind of make game AI out seem to be like this super complex thing of like a million moving pieces and all this like craziness and stuff. And realistically, it's not, but there is this misconception. And I think this is going to piss a lot of like AI programmers, but we're not building AI, and we need to stop pretending we're building AI systems in games. We're not. What we're doing is we're building a simple reaction system, right? We have very orthogonal goals, and fundamentally what we need is systemic and like controllable responses. And we need to focus on scalability, extensibility, and debuggability. I want to add controllability there in terms of like the people that are going to be using systems, designers, gameplay programmer, they need to be able to control what happens in a very explicit and simplistic manner. And they need to be able to adjust this to the needs of the game as the game evolves over development. Now, in almost all cases, game AI is solved through a rule-based reaction system. We have some rules, we apply those rules to the game, and we figure out what the AI should be doing. And that's kind of it. It is fundamentally just information management. We have some data, we look at the data. From that data, we figure out, okay, our rules tell us that we need to be doing X, and we do X. And, you know, a couple of frames later, we do the whole thing again, and we say, oh, now we need to do Y because the environment has changed. If you want to look at sort of more academic information, what is super useful, there's a field of mathematics called discrete mathematics. It's surprisingly, since I moved to North America, like nobody seems to have ever heard of this. It was something that was taught in universities. At least when I was doing my computer science degree, this was a foundational thing. We had several of these courses, which covers things like graph theory, propositional logic, fuzzy logic, combinatorics, permutations, a lot of that kind of basic stuff. And that is the foundation of everything we use in game AI. It's basic logic, basic permutations, combinatorics. Occasionally we'll touch on graph logic, not necessarily a lot of the time. And there'll be a lot of kind of statistics and kind of weighted functions. But as I said, like it is just a reaction system. So it basically just boils down to this: if conditions, then some actions. And it kind of like, you can separate it even further into three basic parts. Like the first is the information that I need, right? That's the conditioned part. Like I need to know something about the environment, the game, whatever, to validate those conditions. Secondly, I need the system that actually evaluates the rules. That's the whole if-then part, right? That's the decision-making aspect. And then we need the final, like the actions. What happens if this rule matches? What do we do then? And that's sort of the actuation layer. And those are kind of the three major things that we need to focus on. And that's what this talk is going to foundationally cover. Additionally, I'm going to be primarily talking about agent-based game AI. This is sort of the approach that pretty much every kind of action game, AAA game, whatever, roguelike uses, where you have distinct characters and these characters are driven by an AI. It's also the area where I have the most experience. So an agent is basically just a character or an AI-controlled entity in the game. And I'm going to be using a lot of examples from action and stealth games because that's sort of what I know. I'm going to briefly touch on this now. We're going to come back to it much later, but there are certain paradigms and use in games to manage these agents. The first one being is something I term agent-centric. I don't know if they've actually got proper names, but this is what I call it, where basically the agents take independent decisions based on what they know about the world. And the second approach is where you have managers. This is kind of the more common approach, where you have a big system that basically says, well, I have my 5 AI and I'm going to tell them where to go and what to do. Another term for this is directors, coordinators, situations, depending on the company and the thing, they have different terminology for this. I'm going to cover this in a lot more detail when we get to it. Before we dive right in, I do need to give a bit of a warning. There is some degree of prior knowledge that is assumed. There is a lot of stuff to go through, and a lot of the stuff kind of depends on itself. I can't talk about knowledge without talking about decision making in some degree, and I can't talk about the actions without touching on anything. So ordering this has been kind of a nightmare. So I'm going to try to do it in a way that makes sense for me. But if you have any questions or something isn't clear, just write in the chat. I'm going to be scanning it and I'm going to reply as I can. I'll try to like clarify anything else. So that being said, let's dive right in. As I said, we're doing sort of an agent-based thing. So the first thing we want to talk about is we need a representation for this agent, right? And I'm going to use, again, what I know from this book. They have a very nice approach for this. And I think it's literally the only way to model an agent, where you have a very simple approach where you have the environment, the agent can perceive the environment. It can then make a decision based on the state of the environment, and then it can actuate that decision through its actuators, or its actions. So it's a very simple loop of input in, decision, and then output through actions. So if we try to formalize this, we can basically split into those three things that I kind of mentioned earlier, where we have the perception knowledge layer. This is the state of the game. What other characters there are, what's a usable object that I can use, is something on fire, is there a sound, those sort of things. Decision making is just a rule evaluation, and actuation is how we interact with the game world. So that can be stuff like animations, barks, like the audio effects, VFX, anything that modifies the game world. This sort of three-tiered model applies to basically any game AI system because they all have similar needs. No matter if you're making The Sims or you're making a racing game or you're making a shooter, your agents need to have knowledge about the world. They need to make some sort of decisions, and then they need to, act on that. The thing that's super important is that each layer has to be considered as a separate thing. And that's something that in most implementations that I've seen, these things get blended together to a point that it's not clear where one starts and the other ends. Each layer should be independent. They should have very little access between them, and the data flow must be absolutely controlled between them. So functionally, what you want to do is you want to say the decision making needs to know about the knowledge, obviously, because it's the if then, right, in that rule-based thing. So it needs to know about knowledge to evaluate the conditions. In very specific cases, the decision making can modify knowledge, but that's not the general case. That's a very limited exception. Fundamentally, it's just read-only. The decision making then also needs to access the execution to basically say, hey, I made a decision. These are the set of actions you need to execute. So I'm going to tell you to run this action. I'm going to wait for you to complete or fail or whatever. And then I'm going to tell you what to do next, right? And so there's a kind of bi-directional flow, but it's in terms of I give you a command, I kind of wait for that to complete, check the states of that, and then when that does, I issue another command, right? It's not a read, write, and kind of manipulation thing. It's like request, send, receive kind of thing. Knowledge should not know about shit, should not access actuation decision making. There's no reason to do that. There's no benefit. It should not happen. Actuation just needs to be told what to do. It has no access to neither the knowledge nor the decision making because it doesn't need to. If I want to tell a character to move somewhere, it doesn't need to check the knowledge. It doesn't need to check the behavior tree or whatever you have running in the decision making. It just needs to move to the position that I've told it to. So we can kind of restructure this in a different approach where, we have the decision making and we have this sort of three-layer thing. So this is kind of what we're going to cover is these three areas. And whoops, sorry, I managed to finish the slides literally an hour before starting this, so there may be some fuck-ups. We're going to start with the actuation and the kind of execution layer first. Primarily because it's also generally the simplest. and the most detached, and there's not too much ambiguity and stuff here. As I've kind of alluded to earlier, it just is acting in the world. So it's doing things like moving the agent, playing attacks, playing animations, interacting with smart objects, triggering audio and VFX, so those sort of things. And as I said, it's basically being directed to the decision making. Something decides I need to move, it asks the action system to move, and the action system then says, well, you need to play this animation. Oh, you have footsteps, so we need to play the footstep sounds. Oh, like you're walking through a desert, so we need to do puffs of smoke on your feet, blah, blah, blah. Kind of the basic realization aspects of a character moving. I have talked about this in the past. I'm going to make the slides available after this, so there's a few links in here that you can kind of like get access to further resources. I've written an article on, that goes into detail about how to, separate AI and animation, how to build some of the structure. What I'm going to do here is provide a much simpler approach, and one that I've kind of gravitated more towards. I've grown over the years. So since I wrote that article, certain things I realized were unnecessary or overly complicated. So I've just removed them and come up with something that, is in a shipping game now, and is generally a simpler approach. So all you kind of need is a very basic system to just register action requests. Move to X, do melee attack, jump here, use a nav link, use a smart object. That's foundationally all you need. You need a system that basically you can issue that request to, you can ask it what's the state of that request, and that's kind of foundationally all you need. The important thing is that they are independent from the AI and that they can be requested from multiple places. This is kind of a very important thing, fundamentally because these days we have a lot more in-game set pieces. We have a lot more kind of cutscenes or kind of what we used to call aquarium setups at Warner. Basically, it's like a mini cutscene that happens out of reach, like behind a glass window or behind a door that you can't get through, that gives you some environmental storytelling or something like that, where you have to script a bunch of movements, a bunch of actions, that sort of thing. And you don't really want an AI for this. You just want the designer to say, hey, I need this character to move to here, play this animation, or use the smart object, or trigger this audio, blah, blah, blah. So in separating this action layer from the AI, you open that up for other systems to use. Additionally, it allows you to generate functional tests for a lot of this stuff. It allows you to test all of these actions independently of everything. That said, they are big dragons here. Because this system is now accessible for multiple areas, you can occasionally get into a problem where multiple areas are fighting over it. For example, like you're transitioning from an AI from gameplay into a cinematic, and the cinematic system is now trying to issue actions while the behavior is still running and issuing actions. And you can get into a lot of trouble there. So you have to handle the transitioning of AI agents between systems much clearer, and you have to have like clear boundaries of who is in control of what when. So the actions themselves, they are very simple. They're just a program that operates, that just executes a set of actions and waits for them to complete. It has explicit start and stop stages to basically acquire resources, set up whatever state it needs to do, and to clean up stuff if it needs to. One thing that's important, and surprisingly it's not very common, is that these actions need to be able to fail. They need to have a result. The environments change. Things can change while an action is running. For example, if I'm moving from A to B, the player could destroy something in the environment that now blocks my path, and now my path is invalid. I need to be able to fail that move. I can't just get to some point and then time out or have the behavior handle a lot of the stuff. It's a lot simpler to just handle this in the action itself and just say, hey, something happened, I failed, handle it on your end, because I'm explicitly telling you that this thing failed, not I'm complete, you figure out what the fuck happened, which has been a bunch of the systems that I have worked in. So I'm going to do a very pseudocode example of something like a move to. If you look at the start, It basically is there to set up character gameplay states, character physics. For example, like lock me to the nav mesh, make sure that I have gravity enabled, put me in the right animation global state. Like, for example, I need to be in the locomotion state, those sort of things. So you kind of say, hey, I'm starting this action, set up my character for me. Then the update is the part that now starts and says, oh, do I have a path to my goal? No. Okay, let me try find the path. Oh, I couldn't find one, so I'm going to fail. Or maybe it's going to say, hey, my path was invalidated because the environment changed and the dynamic nav mesh has updated and now my original path is invalid, so you need to issue a new request. And again, if that fails, we early out. If I'm moving along the path, then I'm checking like, hey, am I within a specific distance to trigger a stop animation? If I am, I trigger it. Otherwise, I just keep following the path. If I'm stopping, I might check the animation and say, hey, animation, are you within a point where you're complete in terms of like, I can now transition to something else? If I am, then I can end the action and say, cool, my action is done. If I'm idle, that means I haven't started moving yet, so I need to trigger a start animation. Very simple things like that. And in the stop, that's primarily there to handle things like, if I have a path handle and I've requested a path and I'm holding a handle onto it, I need to release that. If, for example, something happened and I failed my move to, like I was interrupted or something happened, but I'm still issuing animation move commands, maybe I need to issue a stop, just to make sure that, I trigger a stop animation so the character will actually go into idle properly instead of having that handled in a different system. Again, the stop is more as a safety net if you need it. In many cases, you don't really need to, primarily because of a rule that I kind of have for a lot of this stuff is that every one of these actions need to set up all of the state it needs in the start. You cannot assume that a previous action has put you in a good state. The assumption is that you don't know where you're coming from. You don't know what you were doing beforehand. And when you're networked, it might even be worse because you might have had a lag spike or something, and now you're going from a completely unexpected state into a completely different other state. And so the easiest way to handle this is you basically say, when you start, you literally set up everything that you would possibly need, right? All character physics, all animation state, everything. You basically assume that you've just spawned the character in. This makes it super easy as a programmer because you don't have to worry about where you came from, what state you're in, whatever. You're just like, this is what you need to be doing, done. This was a huge win for the team when we were working with this because it basically removed a lot of thinking and it removed a lot of dependencies. Programmers didn't have to think. They basically said in the start, I need this setup to be set up. Cool, I set it up and I move on with my life. Don't have to think. And as I said, the stop only exists if you really need it. And it's mostly to handle like interruptions and failures. When it comes to networking, the one nice thing of having this thing separate from everything else is that fundamentally, this is the only thing you need to replicate. Decision-making usually runs on the server. A lot of the knowledge stuff usually only runs on the server and exists there, but the actions need to be replicated. The nice thing is that they are relatively small things that are play an animation, move to a position, those sort of things. So they don't really have a lot of state that needs to be replicated per action. And a lot of them are long running. So you replicate a small amount of initial data to start the thing. And then you don't really have to do much. You can run it locally. The one thing that is a little tricky is that sometimes an action may differ whether it's running on a server or a client. So for example, a move to for an AI on the server would do pathfinding, path following, a lot of that kind of stuff. But on the client, all it's going to be doing is saying like, I'm just going to follow whatever velocities are being replicated to me. And I'm just going to move the character as the server is telling me. I don't need to follow anything. I don't need to do any pathing. I don't have to do anything. I just, wherever the server tells me I am and whatever velocity the server tells me I'm running at, that's what I'm going to do. And I'm going to locally calculate my animation parameters to basically try to match whatever the server is telling me. That said, there are times where you have to replicate the animation kind of intents, not necessarily the parameters, but the intents for certain like discrete animations. For example, a turn. If, let's say, we have an AI running down a path, and all of a sudden, halfway down the path, he's told that he has to, turn around and run backwards in the opposite direction. At that point, we have to play a plan to turn animation. It's not a simple turn and follow a path. It's like, stop what you're doing, play this animation, and then repath from your new position. That animation will be calculated on the server through whatever direction the character was in and whatever direction the character decided to go in. And we will say, hey, you need to play a turn on spot, and that covers 47 degrees to the right, for example. That then needs to be replicated so that when we receive that signal on the client, we will say, hey, the server said you have to play a turn on spot, that's 47 degrees. That client might only need to turn 30 degrees or 50 or whatever, right? It doesn't matter. You need to play the exact animation that the server is playing, and then your server position correction will try to over time interpolate and correct the error. But you need to play the right animation, because oftentimes animators will have very different animations in different directions. They might have a 35 frame turn right 45 animation, but they might only have a 20 frame turn left animation. So you need to make sure that you pick the right animation, just to make sure that the character is doing the exact same thing that the server thinks it's doing, as well as the timings and stuff. So I know it seems very obvious, but it's a mistake that I've seen happen so many times that it's definitely worth mentioning. Again, something I mentioned earlier is that the action system is the only system that modifies game state. Decision-making and knowledge, they are not something that interfaces with the rest of the game. The action system is the only kind of hooks out of the AI into the actual game state, and it's the only thing that can modify objects, trigger things, spawn stuff, link to things. And depending on your engine, this may have to run in the main thread. So for example, when we were using Unreal, a lot of the Unreal base systems are not thread safe. So you cannot spawn VFX from multiple threads, because the base actor is not thread safe. So the components get reordered, and lots of things go horribly wrong. So what we ended up doing is we ran all the AI stuff threaded, but all the action still ran on the main thread. So in one section of the editor, all of the AI basically executed their actions and updated what they need to do. Being able to separate this from the rest of your AI allows you to do that. And it's something, as I said, other systems might need to interface with it, and it's generally a good practice to do that. Now, that said, in terms of executing actions, you need some degree of layering. Now, what I mean by layering is that for the most part, you're going to be in one primary action, moving, idle, playing an animation, interacting with a smart object, something like I want to say full body, but that's not entirely accurate. But functionally, you can think of it as a character doing a full body action that it cannot do anything else at that time. It cannot be interrupted. If you want to switch from jumping to walking, you will switch actions. Additional to that, you do need some overlay or parallel actions. Those are things that can occur on top of one of these primary states. So for example, shooting would be a good example of a overlay action, because it can happen when I'm idle. It can happen while I'm moving. It can potentially happen while I'm jumping or falling. There could be state changes to the character that need to be registered that run across all of the states. For example, once a character's health drops to a certain level, you might start an injured action that just fundamentally sets some animation state or some other flags, but it's something that's easy to replicate because your actions are being replicated. So you just replicate saying, hey, start the injured action on all clients, for example. And that needs to run in parallel. So a good example of this is here I have a move to, then the character will stop for some reason, and then they'll start moving again to some new position. But while this is happening, I need the character to shoot. So we'll have a shoot action that starts and ends. Then we might have another shoot action, but it might start in the move to, and it'll only end when the character is already idle. But we don't care because, it's done in parallel. Might run out of ammo, need to reload, and then we might need to shoot. While this is happening, we may end up losing enough health that now we're injured. And so we will start another injured action that runs across multiple of these. This is all you need in terms of the actuation layer. You don't need to overthink. You don't need to do more than this. This is fundamentally what you need. And the reality is you don't even have that many overlay actions. If you're doing a shooter, you're pretty much going to have shoot, reload, throw a grenade, flinch, like a hit reaction that doesn't interrupt the base thing, and potentially some injured stuff or whatever you have that basically is just like a visual overlay. That's it. It's no more complicated than that. Where it does get a little tricky is in terms of lifetimes. Now, this is something that I remember a lot of the gameplay programmers initially struggled with. The action lifetimes do not match the lifetimes of other systems, for example, animation, VFX, audio. Your action is issuing some commands. It is waiting for something to happen and then saying, I am functionally done in terms of a gameplay state. If I was moving, I might have triggered a stop animation, but I'm not going to wait for the full stop to complete. I might say I'm far enough in the stop now that I am stopped. And I will say my action is done. Feel free to do something else. I like to call it a sort of a fire and forget, where the actions will send commands and sometimes they just won't care. For example, like I might trigger a VFX out of an action. I might not care if it finishes, when it finishes, what happens with it. It's just like, cool, trigger the VFX, move on. Audio is another one too. Potentially I'm going to trigger a audio bark. I don't need to wait for that necessarily. I'm like, yeah, I'm talking, but my full body is done. My action is done. I can start something else. This is extremely necessary for things like animation. As I mentioned, the stopping is a common one where we were going to end the action halfway through a stop animation, just so we can start another animation that can then blend so that we still have time in the stop animation to continue playing and then blend out of the stop directly into the next one and not have to go to idle and then from idle blend into the next thing. So if we want to put that on kind of a timeline, we're going to have a very simple kind of, let's think of this as a melee attack. We move to a position, we trigger a melee attack, and then after the melee attack, we're now in idle. So during the attack, we might fire off a VFX, like a weapon trail or something. And that weapon trail might, the lifetime might exceed the lifetime of the attack action. Same thing for audio. We might trigger an audio action. Basically a whoosh or something with the weapon. While that's happening, there might be a hitbox as well. That basically is for only a portion of the attack that we basically tell the hitbox system, say, hey, we need you to create a hitbox here with these dimensions, and it's going to follow this path or whatever. And then at some point, the action will be controlling that and say, hey, I'm done with the hitbox, you need to kill it. Whereas the VFX audio just went across. When it comes with animation, for example, at the end of the move to, we will issue a stop to the animation system. That will start the stop animation. And we will say, hey, I've requested the stop. I'm done. My move to is finished. Don't care. I've issued the command to stop. I don't particularly have to wait for this. And then the attack starts, but maybe the attack has a couple of like a frame or two of saying, hey, I don't have line of sight, or I don't have nav mesh reachability or something to get to the character. So I'm going to maybe wait 1 or 2 frames to see if that happens. And while this is happening, the stop is still running on the character. That animation is still playing. Once the attack issues that request, we then switch the animation state into an attack, which will then blend the stop and the attack together. Right? So we will have, the animator will know I'm in a stop, I've been told to attack, how do I do that? Same thing happens with the attack. I reach a certain frame in my attack animation that the animator flags and says, hey, at this point, you're done with the attack, right? You can leave. They often call this as like cut time or interrupt time or something like blend time. And at that point, we end the attack action. The idle action kicks in and says, oh, well, you need to be in locomotion, and I'm going to request an idle animation state, which will then trigger the idle. And then we will blend from the last couple of frames of the attack into the idle. And in the graph or whatever, they can handle that explicitly and say, oh, I was in an attack, I've been told to go to idle, maybe I have to do something special in those cases. The other thing is that if you remember that each action will set its parameter state at the start. When we're moving, sometimes we want to end without stopping. So we're basically running to a point. When we started this move to, we've said, hey, you don't end in a stop. Once you get to the end of the path, you just end. But you don't change any animation state, you don't change any parameters, nothing. Whatever your final heading facing was, we're going to keep those values and the character is just going to keep running into infinity. You know, that we do because there is an assumption that we are going to start something else after that, right? So for example, if we think about the decision making, somebody's explicitly said, I need you to run and attack instantly without triggering a stop. So I'm going to issue a move to and tell you, hey, I need you to move to there, do not trigger a stop. And then as soon as you tell me you're done, I'm going to tell it to attack. So what's going to happen is we'll start playing this locomotion cycle and the move to is going to end and we're going to keep playing that locomotion cycle. In this case, the attack, as soon as it starts, is going to request, hey, play this animation. And we're going to go straight from the locomotion cycle into the attack. The important thing here is because the move to didn't change any of this state, we have all the previous animation parameters and we're not going to, for example, now, if, for example, in the stop, we went and just said, okay, whenever locomotion stops, we have to be in idle, we have to trigger a stop, we have to clear the parameters, we have to do this kind of, that's going to cause a lot of animation issues. The idea is that like, I leave the move to in whatever state it's in, the graph will switch to a completely different state, but my source state will be left untouched and unchanged. This is kind of a detail for animation. I'm not going to spend too much time. Idle does the same thing. When the idle starts, we blend, everything works. So this is an important thing. Again, I'm going to stress this. Do not tie the action system to your AI and gameplay systems. Pretty much every implementation that I've seen has done this to some degree and it made it basically untestable. Like, for example, me trying to do a move to, it was checking the knowledge and reading values from there. Why? Right? So now if I need to basically just have a dumb agent move from A to B, I need to have a knowledge system added. I need to have a bunch of data set up there. Then I need to add God knows whatever else. It was just dependencies everywhere. What the ideally you want to do is you want to take a character, add the action system to it, and now it can basically be a puppet. That's the goal with this sort of thing. The reasoning for this is you want to be able to build all of these actions completely independently from one another. And you want people to be able to test it. So you want to basically provide a very rough scripting system that you can request an action. And then you give this off to the animator and say, hey, this is how you can request a move to, and this is how you can chain move tos. Now you can test for all the coverage of what happens when I interrupt a move to with a move to within 2 seconds. What happens when after I trigger a stop, I trigger another move to? What happens if halfway through a move to I change my path, right? What happens if I tell it to move only 2 centimeters in front of me? Or maybe I tell it to go 5 centimeters back, but in a completely different orientation. Do we have animation coverage for that? Can the AI do that quickly enough? Is it going to do janky stuff? Is it going to break? They need to be able to test a lot of that without playing the game. And a lot of places, they have to basically play the game and hope that they trigger this fucking thing. If you build a separate, you can test it separately. It also allows you to basically separate AI from the actions. Most places, AI programmers towards the end of the project basically become triage QA, in that all bugs go to them, and then they basically go through and say, that's an animation bug. That's a bug with the action. That's a pathfinding bug, right? A lot of the time, it's not even an AI, but somebody has to go through the AI code to basically say that actually, no, it's animation. But if you separate it out, you can build a test level that just tests the action and have QA run through that every day and say, hey, this thing could go from A to B yesterday. Today, it doesn't reach it. Why? Well, maybe somebody submitted new animations that break something, or somebody changed something and now 2 or 3 of the actions are broken. But now we don't have to waste, gameplay QA or AI programmers' time to basically go through behaviors and check, is it the behavior or is it the action? We know exactly where the problem is. Another benefit is, as I mentioned, allowing other systems to use it. But one thing that we did at one project that was really interesting is that we handed this off to a designer So the designer, instead of doing a PowerPoint of saying, hey, I want an investigation to work like this, and this is sort of the behaviors I kind of want, they basically built a very rough environment and scripted it and said, the player does X, and then the AI should move out like this and investigate in this sort of pattern. And they basically provided a kind of almost a pre-visualization in the game of what they wanted a search to look like, or what they wanted combat positioning to work like, or how they wanted something to do. So it was a very fast way for them to pre-visit, which was a lot better for a programmer because they could look at it and say, okay, I understand. Or they could go with the design and say, what happens this situation? What happens this situation? And they can kind of play it out, sort of like as if they were playing with toys, little Legos or something. It's also really good for reviewing a design because, and I hate to say this, a lot of directors cannot extrapolate from a paper design into something in the game. And so now at least you're giving them something visual to see, and they can at least basically tell you, hey, actually, this isn't what we want. We want blah. Instead of you building something out and building a real system and then being told afterwards, yeah, no, that's not what I thought the design was saying. So, whoops. So in conclusion, it's just a system to execute actions and agents. The sub areas here, these are sort of the domains where things get a bit hairy. It's primarily character physics, pathfinding, avoidance, animation. This is covered by the actuation layer. So I have this backwards again. We're going to jump into the perception and knowledge area now. If there's any questions on any of the action stuff, feel free to dump it in the chat and I can get to it. If there's not, then I'm going to jump right ahead. I wish we were a third of the way through, but we are not. So let's keep going. So when it comes to knowledge and perception, I generally like to have a separate representation of the entire AI world. Hold on, there's a question. Would you consider searching for a path to be part of the game knowledge? No. Pathfinding is entirely actuation because it is only needed for certain things like, getting from A to B. Occasionally, pathing can be useful for parts of knowledge, and I'll give some examples there. But it's not meant. It's not meant for what you would expect to do, i.e., finding a path from a location A to a location B. Move tos do need that information. Decision making may need to do pathfinding in advance to figure out whether something is doable or not. So, for example, if I want to play a melee attack, I want to make sure that I can reach that target on the nav mesh, right? There's no point me saying, oh, let's play a melee attack and then trying to get a path to the thing and there isn't one, right? There's no point starting that behavior to begin with. So there you might want to pathfind, but it isn't generally something that's in the knowledge. So as I was saying, like when it comes to the AI world, it is functionally just an AI only representation of game state. So it's like a big database that a lot of stuff registers into and says, hey, I'm something the AI cares about. Whether it's a character, an object that can be interacted with, some volume that changes something. It could even be internal data that decision-making and AI systems are using or generate themselves, and it's shared across multiple agents, that sort of thing. It is functionally a little black box that has very limited access, both externally and internally, that contains the entire state of what the AI knows. Right. So, for example, like if I give some basic stuff here, I'm mentioning Stims. We're going to get to Stims later, but they're basically just events that happen in the world. So functionally, the AI world just has everything relevant to AI. It potentially has acceleration structures for certain things like every audio event that happened in the game. We want to potentially have that in a spatial data structure so that, when we want to say which agents, need to receive which events, we don't have to do constant crazy lookups and, all your basic, like, am I within distance everywhere? I can just do an octree and just basically say, hey, give me all events within like 5 meters of this agent, and then I can go just through those 10 or whatever instead of going through the thousands that may have happened in the entire world. Additionally, it will be the system that manages the data transfer between what the world knows, which is everything, and what each individual agent should know, which is a very limited set of knowledge. Additionally, it is the thing that is running the AI simulation, all of the updates, sensors, behaviors, decision-making, everything. It does not run the AI, the actions though. The actions, as I said, is completely independent from this system. So the actions will be run by another system at a different point in time. This just cares about AI data and AI sim, nothing else. I mentioned the stims. I think that's a relatively common name. What a stim or stimuli is just an event that's occurred with a specific type, and they're usually tied to a location in the world, and they often have specific lifetimes. So for example, audio stims are a common one. A sound occurs, we say the sound lasts for like half a second, and it's at this specific location, and it's of this intensity. Additionally, the stims could have some metadata that says, hey, I only apply to AI agent of type blah, right? Some places have called it events, some places called it world markup. Stims, I think, is the more common thing. Generally, we have like 2 or 3 categories, visual and audio. They're kind of self-explanatory. What can I see? What can I hear? There's also sort of generic ones, which are things like the last known position of a character. It's not something that's visible or audible. It's just, hey, it's a piece of information. I might generate a stim. The player might leave breadcrumb stims to kind of help AI chase them, because we want to fake a bunch of stuff. We don't really want the AI to be aware of where did the player go. Let me think about how to get. It's like, no, just leave a trail of breadcrumbs that then the AI can follow. Volumes that might basically say, hey, within this room, it's dark. So now your sensor might react differently, or, hey, this room is scary. So now you might have more, fear or whatever. Those are those kind of things. Some places tend to try to overthink this kind of thing. And then you have shit like smell stims and extra paranormals. Well, not paranormal, I don't remember the term, but ESP stims and a bunch of this kind of nonsense. It's like, don't overthink it. Just visual, audio, and blah, generic, whatever. The stims are primarily occurring as side effects. And I say primarily because it's the vast majority are coming as a side effect of something. Like an explosion will trigger an audio and a visual stim. Footsteps will trigger audio. Anim events might trigger, specific visual stims. Like if a character's reloading in the reload animation, you might want to say, hey, for the duration of this animation, generate a volume that says, hey, I'm reloading. So if somebody sees me, I'm reloading. Or it can modify that actor and say, hey, I see this actor and this is the current action that they're doing. LDs might want to put volumes that basically they can turn on and off. So they might put an alarm volume in an area. And if, the player messes up, then, they would enable that volume and then all the AI will magically know that there's an alarm or something. These stims can come from any system and any place. The main thing is that once they are spawned, they will get registered with the AI world, and then we will forward them to whatever agents care about them to a large degree. Now, before we get into how that forwarding works, the main thing we have to cover first is the concept of knowledge. And that is a personal kind of database that each agent has regarding their specific state. Like, what do I know about the world? What's my state? Am I relaxed? Am I searching for somebody? Am I in combat? Am I scared? What is that state? What events have occurred around me? Was it like 10 footsteps around me that, I heard? Who can I see? What objects are around me? Like, what stuff should I be doing? What's my role? Those that kind of like it's entirely personal information, and as such, it's better to restrict access to it that only that agent can read and write to it and nobody else. In some places that I've worked where that wasn't enforced and you had agents messing with other agents' knowledge, and that generally was done to hack a bunch of group behavior or nonsense in, and that basically broke every single time somebody tried to do that kind of an approach to things. So fundamentally, it's like keep personal knowledge to be entirely personal. I think on Hitman we had private and public knowledge, and that was also a giant fucking mess. You don't need any of that complexity. So ideally, just be harsh and just restrict access. Now, as I said, it's just a database. It contains knowledge about what I know about the world. But those entries are kind of interesting. I don't think there is a single structure that can cover every use case. I've never seen one, right? Every time that somebody's tried it, it ends up being some sort of a mess where you have like 5 common variables and then a pointer to arbitrary data. And pretty much all the time, you're just dereferencing that pointer and casting it anyways, right? And then half those values are just being ignored. And in kind of the goal of being generic, you end up with a very inefficient system because now you can't specifically structure your knowledge in a way that's efficient. And I'm going to touch on that a little bit later. Now, I'm going to give you an example, for example, a stim. Stim is a very common thing. So what would we need to know about a stim? Well, we'll have a struct that basically says, what's the type? What's the severity, intensity, scale of it? Where was it? What's the lifetime for the stim? Because audio stims might have a lifetime. Visual stims might not. They're either visible or not. It's binary. And potentially an ID saying like, who caused the stim? Was it a different character? Was it a player or whatever object triggered this? You might want to have a link there via an ID or something. Now, the very common approach for this, for representing agent knowledge, is a blackboard. Blackboard is simply a key value store with arbitrary data. And it's a completely generic solution. So, put whatever I want in there, becomes fundamentally a giant garbage dump of things. And generally it becomes a giant performance headache as well. Because during our AI updates, both through sensors and decision-making, we go through a lot of data, right? There is a lot of stuff to be checking, like, did I hear something? Where did I hear it? How far away was it? What type was it? What can I see? Who can I see? What are they doing? And all those kind of things. And you end up just constantly scanning through these keys, right? You basically just keep searching either for keys, or you keep saying, I need all audio stims. And then I go through all audio stims. And because it's a big key value store, the underlying data structure may not be linear, depending how it's implemented, who knows? It might be because it's arbitrary data. Every value is a pointer to something else. You're constantly cache missing or dereferencing random stuff. And this is primarily a side effect of the overgeneralization, because you have very specific access patterns, but a blackboard will never match those because it is meant to be just key values. And that's kind of it. So personally, I prefer a more explicit structure. Yes, it's less flexible in some ways, but it allows you to have things like, hey, all my stim entries, I know that they're stim entries. So I can split them by, these are all my audio stims, these are all my visual stims, these are all my generic stims. And if the stim type has additional parameters, like it might be visual stim / character / enemy or something, you can do further categorization or fast lookups. You can order them potentially by newest to oldest to closest to furthest, those sort of things. If you know that that's something that you're doing a lot, for example, you want the 3 best covers closest to me. You might want to sort all the cover entries by distance, and in the 10 behaviors that are checking for cover, you don't need to, do that search 10 times, or come up with another system that then caches queries to the knowledge, and then you access that from multiple places, and then somebody has to clean that. And right, I've seen these sort of hacks being built to improve performance. on top of a blackboard, where they basically build a cache that sits in between your behaviors and your blackboard, which is sort of the worst of both worlds now. It's like, yeah, it fixes some issues, but it adds a whole bunch of other ones. The other thing is that I tend to do something called goals. I'm going to go into detail on that later. It's a very, maybe the name is bad. It's what I called it because it makes sense to me. But when we cover it, it's not technically what maybe a lot of people think a goal would be. And that's more of a compound arbitrary entry that provides a huge amount of data that will optimize a lot of these access patterns. Another problem is, especially with the blackboards approach, is that that data tends to be externally accessible. And that can be problematic because now you don't have control of who's writing to it, which, like, the most basic problem is that you can't really parallelize this because anybody can write to it, whatever. But the other problem is that other systems could change something that you need, or remove something, or add the wrong thing in at the wrong time, or put that entire knowledge state in an invalid state where some aspects are valid, but other things that they depend on are now in an invalid state because somebody went in with a level script and just modified 2 of the 3 things that they needed to because there is an implicit dependency between three entries, you know. And this is why, again, I'm kind of hammering on the whole, like, controlling access and when to limit the access. There were many places that I saw where, for example, the inventory system was going into an agent knowledge and telling it to pull out a weapon. But then the action was also telling it to unholster a weapon. And so you would end up with this, like, because the timing was off on those 2 systems, and you would end up with a double unholster request because 2 systems were messing with the same thing, and it was done at different times, and nobody really knew who owned what, and those kind of problems. So you can avoid a lot of that pain by just, having strict rules. Now, how do we get stuff into that actual knowledge? There's an update. The update runs occasionally. It doesn't have to run every frame. It's actually better that it doesn't. You can run it at a relatively slow interval, 100 milliseconds, 150 milliseconds. It's fine. We have 2 primary things to fill the agent's knowledge. The most common one that everybody's aware of is sensors. And then the goal generators are basically like an advanced sensor. It's just because they're slightly different in the case of these goals that I have. So the other thing that's important is that you kind of want to do all the knowledge updates on a single frame. In the past, I tried to be smart and kind of schedule like different sensors on different frames and all that kind of stuff. And it just adds a lot of complexity and a lot of headaches that you really don't need. Fundamentally, you just say, you know what, I need to update this agent's knowledge on this frame, run all the sensors, run all the shit, and boom, I'm done. I've got a full reflection of the AI game world at this point to the agent. I don't need to now sort of like load balance visual and audio sensors and all that kind of shit. If you find yourself in a situation where you have performance problems and you think that that's a good idea, then now I basically run my visual sensor one frame, my audio sensor, and I think like you need to figure out why the hell you have the performance issue in the first place before you start doing something insane like that. Generally, sensors should not be expensive, and you shouldn't need to do any of this kind of stuff, especially on modern hardware. The other thing is that frequency that they run at doesn't need to match necessarily the decision making. Decision making is always pretty much running on stale data, unless you literally tie it to you run it every frame, and every frame you reflect game state, every frame you run decision making. If you don't do that, it's always going to be stale in some form or other. And it usually doesn't matter because your AI behaviors are not changing like 5 times a second, right? Most of the time, they'll change once a second or something in the worst case scenario. Most of the time they'll play an animation and then switch state and then finish that thing and then switch state. You have time, use that time. So an example of that might be is like, we'll do a knowledge update on agent 1 on one frame, might do a knowledge update for agent 2 on another frame, might run the decision making there for the first one. Then we might trigger the knowledge update for that agent again while we run the decision making for 2. Now the knowledge update for agent 2. Then maybe now the timing lined up and now we run the decision making for both agents on the same frame and so on. You can be flexible with this. It's not a big headache if you want to do this. It allows you a little bit of leeway there in terms of like, what's the word? Sort of in terms of when you want to schedule things. That said, you probably want the decision making to run it at a much faster rate than your sensor updates, because a lot of times actions will complete and you need to basically evaluate what you should do next on that thing. Generally, if you can, I would run it every frame, but I would keep the knowledge at 100 millisecond frequency, potentially. It all depends on how heavy decision making is and how heavy your behaviors and stuff are. In our case, they were very light, so it was a non-issue to just run it every frame. But the knowledge was a more heavy operation because it was tying into doing a bunch of physics queries and a bunch of stuff like that. So that one had more of a cost, and it was beneficial to spread the load there a bit. So speaking about sensors, they are the primary mechanism of transferring information from the AI world into the agent's knowledge. They are the things that create knowledge entries for things like Stims, visible objects, agents, that sort of thing. Again, data access wise, they should not modify anything except the agent's knowledge, not the world state, not the game state, nothing. The nice thing is that if you follow these rules, you can parallelize all these sensors. They can potentially read from the game world, but they should never write. That kind of comes into, for example, doing physics queries and stuff. You know, you can lock the scene for read and spam a bunch of physics queries across multiple threads, and it's fine. So that said, the sensors define the rules for what information makes it into that specific agent. They're acting as filters. So for example, you might have invisible characters in the game, and you know, a specific AI archetype has magic goggles and they can see those specific invisible agents, but nobody else can. So their sensor might have a tick box that says, I can see invisible characters. You know, whereas by default that tick box is set to false and nobody else sees them. So your sensors to some degree can affect what that archetype knows about the world. And this is an area of customization, of being able to provide variability of archetypes, that kind of thing. There may be different sensors for different agents and different archetypes. Again, game requirements will dictate that. One thing that is important is that the sensors may change based on AI state or environmental modifiers. So it's very common that an AI will have a specific set of sensors when they're in a casual or idle state versus when they are in combat. Additionally, they may be environmental kind of modifiers that basically say, hey, the environment is noisy, so my hearing range has been reduced drastically, right? And that might be because they're in a volume or something that an LD sets up. So there will be things that modify those rules. It's rare, but you need to support it because these days games have a lot of edge cases and stuff. So let's go through the examples of some of these common sensors and some of the kind of big headaches that you might hit. So visual sensors are generally a relatively simple thing. It is, what can I see? Fundamentally, they are done through a set of exclusion shapes. For example, you're going to have a long cone or a box or something in front of you. You might have a shorter, wider one to simulate sort of peripheral vision. And then you may have a small little 1 meter thing behind you just so you have kind of like a personal space. So, you know, you don't walk literally up to an AI like right behind them and they don't detect you. Those sort of things. You may have different detection times within each zone. You may have different settings per shape, all that kind of stuff. It depends on what kind of a game you're trying to make. So what ends up happening is when we run the visual sensor, the AI world has every visual object registered with it that the AI could potentially care about. And then we just run through every visual object against those shapes. Whenever something passes, we can then run additional visibility queries. For example, like let's do some raycasts and say, can I actually see this? Because it might be in the shape, but there might be a wall blocking between us, blocking the two things. And this is where, for example, the visual sensor could get expensive depending on how many visual objects they are and what sort of raycasts and ways, you're trying to, how much physics query you're trying to do in that frame for that character. One optimization that you can do is you can use your nav mesh as sort of a cheap line of sight. If an object is straight line reachable on the nav mesh, you are pretty much guaranteed you can see it. Now, that said, this assumes your nav mesh system is fast. If it's not, maybe it's not an optimization. I would profile this. Generally, I prefer certain middlewares for that kind of stuff. And there it is definitely a optimization, just to do a quick nav mesh line of sight. So keep that in mind. It might be an option for you too. Now, where we have issues is we have potentially stuff like this, where a character is partially occluded. They're behind a lamppost. They're behind some piece of LD art that's been placed in the level. And technically they are visible, but if you do a simple raycast like the chest or something, it may be blocked. There were talks on how to do this properly. Generally, the most common approach is you raycast to a bunch of different bones on the character. And if any of those are unblocked, you treat that character as visible. There really isn't any kind of smarter solution. If you want to talk about accuracy, there's a bunch of kind of insane approaches where you do a software renderer and then you do, check for pixels and stuff like this. But fundamentally, just do 5 raycasts. They're really fast. They're really cheap. Just get it over and done with. That's a kind of common thing. Special cases, as I said, in combat, sometimes you may need different setups. So let's say you're doing a brawling game. When the character is in idle and kind of navigating around, you might want a combat sensor, a visual sensor that looks more like this. They're patrolling. You want to have a bit of stealth gameplay where, you can kind of go in and out of their cones, kind of like hide and out, get the kind of detection little bar above their heads and all that kind of stuff. But when you start a fight, you don't want them to lose sight of you as soon as you cross that threshold or go a little bit outside of their, sensor shapes, or even worse, some combat animations might put the head in weird locations or put the chest in a weird orientation. And usually those vision cones are either tied to the chest, which is generally a more stable kind of direction, or they're tied to the head, which in combat will be flicking around everywhere. And so you're going to constantly lose sight of your enemies. So generally what you want to do at that point is you just have a big bubble that says, hey, I'm in combat, so everything within 5 meters is visible to me, even if it's behind me, right? And as soon as something leaves that 5 meters, maybe I still have a kind of a distance vision that is based on my head, but fundamentally, I do not want to lose sight of anything close to me. That is kind of a very common approach that isn't really talked about much, surprisingly, and I've seen lots of programmers make that same mistake where, we build a thing, it works great, and then we get all the weird bugs like, well, they keep losing me in combat. And so they switch back to search meanwhile there's a fight going on. Audio sensors. This is a giant clusterfuck, honestly. Generally, they are distance-based. You hear a sound. I want to make sure that the sound is close enough to me that I can hear it or whatever. The problem is that it's just a massive, massive pain in the ass because you have things like low walls that, for example, the player might not be able to cross or jump across or whatever, but they should be able to hear it. For example, like there might be a chain link fence that the player can climb, but there's a sound, the AI can climb, but there's a sound on the other side that they need to be aware of. But that could also just have been a wall with a roof, so now you can't hear through that wall. Like, you have all these edge cases of like, well, there's a sound, can I hear this? What if there's a window? Does that window affect sound propagation, attenuation, a lot of those kind of things? Generally, I would try to limit reliance on audio as much as possible within a game because it's such a pain in the ass. to deal with. One common approach is that people will use nav mesh distance to basically fake audio attenuation. They'll basically say, hey, there's a sound, how far is it in the nav mesh? If it's within some range of nav mesh, I can hear it. That breaks down as soon as you have verticality in your levels. So for example, a common issue is that you have multiple floors. There's a sound on the upper floor. You do a pathfind to it, and now it says, oh, it's actually within the distance. So maybe I can hear this now on the floor above me. Is that valid? I don't know. But, my rule said I can hear everything within 10 meters. Well, now that 10 meters is satisfied, but is this what we want gameplay-wise? Don't know. Another headache is, well, even if I do the nav mesh thing, what's the closest point to a sound? And a lot of times people forget that we have 3D environments, and this was an actual bug. I still remember that somebody triggered a sound on the roof downstairs. And we said, what's the closest point in the nav mesh? Well, we got the floor above it, not the floor below. So what ended up happening is, the AI decided to investigate the upper floor and not the lower floor where the sound was, and then now you have to handle of there was a sound. What's the closest point in the nav mesh? Am I below a ceiling? Am I above a ceiling? Is it the closest thing? Is it the closest thing down? Is it the closest thing sideways? So now you have to do a bunch of processing to figure out, even if they hear it, where the hell do they go to? Question is, couldn't use the distance returned from nav mesh. That's the problem, is that depending where that is, it might be to the side. It might not be purely vertical. It may be sideways. And now it's do I go straight down? Do I look slightly to the side? You have to do a bunch of processing, especially if it's something like there's a ledge where you trigger a grenade explosion midair or something. And now technically they can walk to the ledge and it's a good spot, but they could also go directly below the grenade. It's also a good spot for it. What's the right one? Yeah. Have fun figuring that out and trying to figure out something consistent and reproducible and whatever. So that's generally a giant pain in the ass. Additionally, imagine that was a catwalk, right? So now I have a sound up there, but it's a catwalk. And again, this is an actual example from the game. So you can see through it. It's directly above you. This is not the right thing to do, because now that might fail, but it's literally a meter above me. There's a guy, firing off a gun, but nav mesh tells me it's 20 meters away because I have to go up a staircase and around a corner and through a door and whatever else to get there. Euclidean distance says, no problem. And now you have a problem. Now you actually have a big issue of what do I do in this situation? How do I know if I can hear it or not? Right? There's a bunch of hacks and, workarounds and all this kind of shit. Ideally, what you want is a 3D volumetric search. You basically want a 3D nav mesh that takes into account things like windows and stuff, and then you basically will do a proper 3D pathfind that takes into account windows and whatever else, that basically says, okay, I'm going to slow it down or whatever. The way that audio works for players, and I'm assuming you're asking, we figured out for the audio listener, we use for the player. It's a different problem set between audio occlusion, for example, like what Wise does in levels, versus what you need for the AI. They really, I don't know Wise that well, but I don't think there's an API where I can say, hey, find me the exact attenuation distance between this point and this point, taking into account every sort of wall and window and everything else. And a lot of the time, those volumes have to be hand placed, which is kind of painful. There was some solutions years ago to solve this problem, but nothing really came of it. And for the most part, people are just hacking their way through it with kind of stuff. I was always interested in there is this middleware package Mercuno and stuff, but potentially you could use that to do a quick pathfind, but again, it's not exactly the lightest thing in the world. Yeah, 3D nav mesh would potentially be overkill. Memory can be heavy, but it can also not be, depending on the format that it's stored in and the granularity of the blocks and your environment to some degree. It depends. Mercuna exists. It has 3D nav. It's not exactly cheap, both in memory or in perf, but it's potentially an option that can solve this in a more accurate way. That said, very few games actually care. Hitman, yeah, there it matters. Call of Duty, don't think it matters. You're not doing stealth gameplay in a Call of Duty or a Destiny or a World of Warcraft or whatever, so you probably don't need any of this stuff, right? When you do need it, then you need to kind of think a bit harder. But again, very few games actually give a fuck about this. So that said, moving along from Stims. So goals are another type of knowledge entry that, it's a concept that I kind of came up with the folks at Warner when we were kind of solving some of these problems. Basically, all they are is a compound knowledge entry. It contains a whole bunch of very kind of bespoke data needed for that specific goal. And by goal, I mean operation or thing that it can do. It's not a standard concept. I haven't really seen this many places, so I don't know if there are names for it or if people actually do this kind of thing. Basically, what a goal is, it's saying like, here's some information about a specific thing you can do. It doesn't need to be acted on. It's not a directive. It's not saying you need to do this goal. Like in terms of a planner, when you have a goal, that's the thing you're trying to solve for. This is not what it is. It's basically saying I have a combat goal. So in my combat goal, I have every single enemy I can see listed in there, plus every single maybe combat interactable or something. Maybe if I have an investigation goal, it will tell me here's all the points of interest that you can search within 10 meters. And that's a search goal. It's basically saying here are things that you can do, plus all the information you need to do them. But it's not something that you have to do. It's just more complex data. Goals also have lifetimes and they can expire. And that's a very important concept for something like a reaction. So if, let's say, I hear an explosion, I might create a goal that says, hey, you need to do a combat reaction to an explosion. But the character might already be in combat. So that reaction might not happen, although the character could be getting shot and it's more important to play hit reaction at that time. And so that reaction might expire in 3 or 4 frames, right? It's there, the information's there. If we can act on it, we will. If it's not, then it's going to just go away. Additionally, if we do act on it, we can potentially also flag them as, hey, I'm done with this, so it can get removed. The things that create goals are fundamentally just advanced sensors. We separated them because we needed to make a distinction between sensors and goal generators in terms of like architecture and stuff. Fundamentally, again, it's a rule-based approach to generate entries, and they fundamentally use what the agent knows about the world, additionally, as well as whatever is in the AI world state. So it's combining personal knowledge as well as world state knowledge and then inferring goals from that. And as I said, that we kind of generate and refresh them every update. So anything that's kind of expired or is invalid or completed will be removed. So some examples will be like, as I said, the explosion gunshot. Additionally, if you can see enemies, we might do a combat. If we have covers, your cover system, for example, might say, hey, there are covers within you, around you within 5 meters. So I'm going to create a use cover goal, and here's all the covers that are within 5 meters of you, right? So I don't have to go to the cover system and say, hey, give me all covers that could be within this range, whatever, right? It's basically telling me, if you want to use a cover, here's all the information you need to do it. But the important part is It is not telling you to use the cover. It's saying if you want to use the cover, you have all the data there for you. And that simplifies a lot of the decision-making stuff later on. And again, like, why even have this? It's twofold. It simplifies decision-making, but it also greatly improves your access patterns. So I'm going to use the cover example. Let's say we have a cover system, we have an agent. During the goal generation, we say, relative to where you are, give me all covers within 5 meters of reachability. I get those covers, I create a use cover goal, I put it inside that agent. That agent might have like 10 behaviors that involve cover information. And those behaviors will initially check and say, for me to even run, I have a precondition that I have a cover goal. If I don't have a cover goal, I'm not a valid behavior. If I have the cover goal, cool, I have all the information needed. Whereas in a more traditional system, each one of those behaviors might be going to the cover system and saying, hey, cover system, give me all covers within 5 meters. Hey, cover system, give me all covers within 5 meters, 10 times in a row. And you're going to have to do that work 10 times. And again, once people start optimizing, then they start building caching mechanisms and other things to share data and all this horrible stuff where they'll start using the knowledge as a temporary blackboard where every query will be cached there. So you could always look there and see if there's a previous query that you can use, but then you can just get a different one with a different range. And it becomes a big, big mess and a lot of complexity, especially once your AI number of behaviors, number of scenarios grows. It also greatly improves the debugging and the robustness of your AI because you can debug the goal generation completely separate from the decision making, right? You run your knowledge update and you see what goals are there and you figure out why they exist and why they're not and why the data is wrong or correct in there without even touching the decision making aspect. It's entirely standalone and debuggable within that context. So a lot of times when we had issues, it was really fast to figure out because we got into decision making, realized the goal information is wrong. And then it's like, cool, go into the goal update and it's like, yeah, I can figure out what's going on, right? I don't have a lot of these queries done in the individual behaviors or decision making process. So it kind of simplifies that. The last thing that's sort of really important is something I call shared information. This is sort of global shared state that a lot of agents can access and use. So it can be accessed through sensors of the goal generation. It could also be accessed directly through decision making in certain scenarios. It basically allows us to optimize and share processing costs in terms of systems where we need coordination or need to reuse a lot of this kind of data across multiple agents. But it could also be used to actually facilitate certain faking of group behaviors, a lot of those sort of things. I see this message saying Splinter Cell Blacklist uses this thing called TAS, which basically nodes with links in 3D. Yeah, I've seen, that's what I mentioned, that there was stuff like this back in the day that existed. If you are already setting up audio volumes by hand, it's very easy to piggyback off that by creating a sort of a waypoint map in 3D for audio. It fundamentally can give you sort of the granularity is kind of high. So it's sort of like a broad face initially, which I think is good enough. And then you can kind of figure out like within that, if it makes sense. But again, it implies that somebody's gone and set that up. And for an open world game, that can sometimes be really painful. It depends, again, how many volumes you have, how the audio propagation works, and a lot of that kind of stuff. It's all situational. And again, the question I would ask, first of all, is, do I really need it? Right? So coming back to the whole shared information, a good example of that would be something like a search. So we might have a behavior that's like, hey, I need to search for the player. I was chasing him, they've disappeared. I don't know what to do. Let me try find him. So we have an agent, they're looking through the environment. We might then generate a search zone, which is within the AI world. There might be a search manager or something else like a search zone system. We basically said, hey, a search has been started. This is the area of the search. let me look up pretty much every single search interaction. Maybe they need to look under a car, they need to look in a dumpster, they need to look behind something. You know, those are all smart objects or like interactable objects within the environment that the AI can use. So we will just find all of them and track them within that zone and say, cool, like you're registered within this, this agent is using this specific search zone information. And every time it does a knowledge update or a decision update or whatever, it can just reference this information and say, hey, here's already pre-cached information for me. For a single agent, this doesn't really make a lot of sense because you could do that in the behavior. It doesn't really matter. But what can also happen is that as the agent goes in and searches an object, it can flag it as, hey, I've seen this already. And then what might happen is a second agent might join that search through propagation or whatever. And at this point, they are registering within the same search. And they're saying, okay, you've already searched those objects. I don't need to handle them anymore. It doesn't assume that the search is the same. It assumes that the search is localized and that when an agent tries to trigger a search, it checks that it is within the same search zone. And if there's multiple search zones that are overlapping, generally they'll get merged together into one. Again, that's more like, you know, for a multiplayer game. Single player, you're generally not going to trigger multiple searches within the same area of the map. Due to, you know, basic physics, like the player's not moving that fast or whatever else. The example of the agent with the magical invisible seeing goggles. Well, yes, whether they register with the search is a whole nother question. That's more of a, my assumption here is that there was a search going on, another agent joined the search, maybe because they were already chasing the player and they turned the corner late and now they're within the same search zone, whatever. The assumption is that they are flagged to be within the same search and they are cooperating with the other agent. And now you have the shared state for that given search. And while agents are searching within there, they are basically sharing, I have searched this object, I have searched that object. We're not going to basically, you know, have 5 people check the same dumpster at the same time, you know, one after the other kind of thing. It's a bit of an artificial example. You'll need a little bit more complex stuff to handle this sort of thing. But that's kind of the idea of having the shared info. Additional examples would be, for example, covers tend to be, you know, like when you use cover in a game, generally picking a cover also involves doing a line of sight check, which can be relatively expensive if you have a very cover-rich environment. So if you have like hundreds of covers within a small area, it can be really expensive to figure out, hey, find me a cover that gives me protection and I have line of sight to the enemy. So what can often happen is that you can generate the shared information and say, hey, there's a combat zone in this area. So I'm going to run in the background and start pre-processing line of sight information for specific covers where there's agents nearby. And basically, I'll make that, you know, that sort of information available to multiple agents to use. This is not something you can generally kind of cache because I know some places they'll actually cache the line of sight information from cover to cover. That can sometimes grow in terms of permutation, the amount of memory you need. But additionally, you only need line of sight information to agents. So it's like, I need to know if this cover has line of sight to those 3 enemies. That's all I care about. I don't need to care about whether it has line of sight to every other cover in the room or anything else. So again, this is something that can run in the background. It doesn't need to necessarily even have agents in it. It's just if combat starts, this thing can start up in the AI world and start churning in the background completely asynchronously and start generating information that agents could use to make decisions. It could be used to do something like, if you're making a brawler, the kind of what's a good position for me to be in relative to my current position and the enemies, right? Kind of make sure that they're sort of circling you or whatever else. It's just a mechanism to share data across other multiple agents. It is not a manager though. We'll come back to that later. This is not making decisions. It is simply just data, that, environmental data, saying, hey, if you want to know information about the environment or whatever else, I have that. You use it however you want. It is not making decisions. It is not telling agents what to do. It's just saying, here's data, do what you will. Like in the third example, if one agent wants to check the same dumpster 5 times in a row, you can do that. That's, it's not that system making that call. This all brings us into decision making. And I love how every one of those slides was wrong. I guess copy paste is a bitch. So coming onto the decision making aspect. What is decision making? Technically, it's just deciding what set of actions an agent needs to take given the current state. We have primarily 2 ways of solving this problem. The one is sort of the more traditional reactive systems, behavior selection mechanism. That's like running a behavior tree, checking a state machine, running some rule-based system, that kind of thing. The other approach is to actually have a planner. And we're going to discuss both of these sort of in comparison. The basic one is the one that most people should be familiar with. It is literally like, I'm going to react to whatever I know about right now. So it's more like I have information, I look through the information, I have some rules, those rules match my information, so that tells me that I need to do certain actions. This kind of, in these sort of systems, you also have now the distinction between the selection of what I should do, as well as, okay, now I've selected that thing, what is it that I should do? Sort of the behavior authoring versus the choosing of behavior. Common approaches for this are, as I mentioned, state machines, decision, behavior trees, potentially utility selection, that sort of stuff. It's very simply pick a set of actions that make sense right now. Planners, on the other hand, they take a specific goal and not the goal that I mentioned earlier, like with the thing, but they actually have a specific goal, like kill AI, kill enemy X. And then they will go through a set of rules or algorithms or whatever and generate a set of actions that will achieve that goal in some manner. There is an implication there that the goal exists before the planning can occur. And this kind of also needs a kind of goal generation step a lot of the time, because to plan, you need an endpoint. To get that endpoint, you need to, again, have a system that generates that endpoint of saying, like, I need to get here. So how do I get there? Well, I move there, I play an attack, and then that solves this goal. So if you kind of like take a step back and you think about this, what is it actually solving? Well, it's solving to a large degree the behavior authoring aspect. It's saying, I will let the system figure out what set of actions it needs to do, instead of me saying, oh, you want to punch that character? Well, you need to do a move to, face direction, trigger punch animation, and then do combat idle. Versus this saying, oh, well, I have a big graph of actions and I am here and I need to get to here in my graph, and that takes me through a move to node, and that takes me through a punch node, and that takes me, that's all it's fundamentally trying to solve. And it ends up being this super high complexity thing that's often a black box and people have zero control on it. If we want to kind of compare the two, sort of, let's come back to initially the goal of what we're trying to do. We're trying to facilitate gameplay. We're trying to present a toy to the player. Designers want predictable responses to actions. When the player does X, the AI should respond in this specific way. They also want to be able to handle special cases. And that is a big thing that a lot of AI programmers and stuff forget. We have so many edge cases, like on some specific level, something happens and now the archetypes need to be behaving in a different manner because they're mind controlled, or they have a special ability that only happens in this level because of some boss or whatever else. And you need to be able to have a system that handles this in a clean, simple way that doesn't require you to duplicate all behaviors or archetypes, all this kind of shit. Like, and that's been the reality of every place that I've worked at. Is it's been a giant clusterfuck every time we had a lot of these kind of special case stuff. Like, especially when you want to disable a previous behavior and add a new one just for one thing. And this is where planners completely fall apart, because they tend to be these sort of like black boxy, like systemic things that have very little controllability, especially given who the target users for these things are supposed to be, which is these days primarily designers, right? You're saying, oh, I'm going to build you a black box planner and have fun. Oh, it did something weird? Yeah, I don't know. Don't know why it did that. Oh, well, right? And so you end up with a high maintenance cost too, because now the only people that can debug this is programmers. Have to go and then say, well, I've got a bug. It did the wrong thing in this scenario. Now I have to replicate and figure out why it picked what it picked and why it came with this. And in the special cases, it just becomes hacks upon hacks of putting magical flags that say, oh, it's now in this level, so I need to go through a different path or a different planning algorithm or bypass something. And realistically, like, again, what is it solving? The behavior authoring. Like, if anybody says, oh, planners are smarter than come with emergent behavior, it's bullshit. Like, it's yeah. I don't see the benefit apart from like somebody's ego of saying, I built a planner. Yeah, AC Valhalla is using a planner. I mean, Deus Ex is using a planner, and Deus Ex had some horrific hacks. Like, when they wanted to stop an AI going to a specific area, they couldn't control it, so they had to literally disable the nav mesh in those areas because they couldn't get the planner to tell it to not go in that specific room or whatever else. There's another question. How to avoid coupling of AI to animation for responsive combat? Play a stagger animation if during a sword swing it hits a shield, you need to stagger ASAP. Those are generally not a problem, because what will happen is as soon as that sword hits the shield, there will be a collision or a hitbox detection that will trigger a reaction stim. Okay, that's something that I didn't cover. Certain reaction stims have to be immediate. They have to be flagged immediately, and they bypass the general sensor update. So your knowledge update is a little bit split. Your general one about doing visibility checks, all that kind of stuff can run like lagged, but things like hit reactions, bullet hits, explosions, that is instant. And that's where, for example, your decision-making running every frame is also necessary, so that on the same frame that you detect the hit, you will switch behavior into a stagger or an interruption or whatever you have. Again, assuming that's the kind of game you're trying to make. If you're doing the Sims, you don't need any of that stuff. But yeah, for those cases, it's not really a decoupling it's not coupling animation to AI, it's coupling a stim to a behavior switch, which is not really coupling, that's the general case. And that's sort of the view you kind of need to take. A lot of the stuff is hard to sort of discuss because there are like so many different kind of game genres and scenarios that it's hard to kind of come up with, hey, these are rules for like everything that works. So the idea here is that I give you kind of a high level overview, and then based on people's feedback afterwards, I can kind of dive in deeper on very specific topics. Coming back to the whole planning thing, like I've seen HTNs, I've played around with them. I've played with Gope and Strips and whatever the hell it is. The other ones that became more popular, I don't even remember the name, the thing that succeeded HTN. I've never found a use case where I'm like, I can't just solve this through a basic like rule-based thing and a behavior. And to be honest, a lot of the time the designers want exactly that. They want controllability. And this is where we have to have like a real discussion between devs and players, because devs, especially AI programmers, have this top-down view of the game of like, oh, we're going to do super cool like flanking behaviors and combat positioning and staggered kind of movement and blah, 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 whatever. And all the player sees is like a third person view with a bunch of AIs moving towards them. They can't see that they staggered the movement in a top-down fashion and they picked right behavior. They just see a bunch of characters running at them, right? And then it's like, cool, you spent months on this like fancy combat system that does all this cool shit, and the player just sees a bunch of characters running straight at them. Great. Good job. And I was guilty of this. This was exactly the mistake I made when I was working on combat for Hitman, is that, I wanted to do super cool scoring of tactical positioning, all this kind of shit. And in the end, I just had a bunch of headless chicken characters running at me. At least that was the impression you see as a player. Meanwhile, the system is doing cool shit under the hood. And so the reality is, like, frankly, nobody gives a fuck what the dev's view is, right? It's all about what the player sees and what the player experience is. And a lot of times devs get really focused on this kind of theoretical approach to, oh, we're going to do this cool like behaviors and we're going to be smart. It's like, no, hold on. As a player, what do you need for gameplay? What is it that would make this combat encounter more exciting? And I can guarantee you it's not going to be fucking flanking and, staggered movement and all this kind of shit. So, and once you kind of get out of this mindset, you realize that a lot of these fancy systems that you thought you needed for like tactical positioning, you don't need them anymore, because the reality is, to get fun gameplay, you often get by with the simplest approaches to things. You might not even need to do tactical positioning. You might just need to say, pick the closest cover and shoot at the player. And that might be completely indistinguishable from, oh my God, let's pick the correct cover that has line of sight and has the right positioning and is scored correctly based on distance and range. And it might just be good enough to just say, pick the closest cover and shoot at the player. And there you go, done. So like coming back to the whole reactive versus planning, my viewpoint on dev has changed over the years. Call me jaded or cynical, I don't know. But the reality is, especially if you're starting on a project early on, the only thing that you have to think about and the only thing you have to focus on is like you have to plan for change. You have to plan that everything's going to change, because that is exactly what's going to happen. You're going to have the initial pitch for the game, and then within a year, everything's going to be like different, right? As soon as like, what is that stupid saying? Like, no plan survives first contact with the enemy. That's true of like game dev. So the thing that you have to make sure is that whatever you build can be changed. So you need to focus on whatever's the simplest approach, whatever's the most obvious for a new user to understand and to reason about, and whatever's the easiest to debug. You also need to focus on systems where the cost of authoring the content is low, because realistically, you're going to be redoing that content multiple times as you learn what the game is, as you figure out, as you're dev testing, as you're play testing, you're going to be doing that content. So sometimes the more manual, like authoring behaviors, if it's fast and you have good tooling and it's easy to work with, that is a much better proposition than trying to automate it with some black box planner thing that as soon as you have to redo some chunk of the gameplay, you're fucked and you have to rewrite the whole thing or restructure it or rebalance it or whatever. Whereas a designer can go in and just author a couple of new behaviors and boom, you're up and running in 2 seconds. So often people will say, don't overthink things, don't over-engineer, blah, 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 whatever. I don't necessarily agree. I think you do need to overthink things a little bit, and you do need to kind of think ahead and try to not over-engineer, but what you need to do is you need to try to predict how things can change. So given your current system and your current design, sit there and say, okay, we're making, AC Valhalla, and we've got a kind of Dark Soul-y combat, and, it's kind of RPG-ish and blah, blah, blah. What happens if tomorrow the game director comes to me and says, I want Batman Arkham combat, like rhythm gameplay combat, basically like the original Assassins. Now we're going back to that mode. Will my system handle it? What do I need to change? How much is that going to cost? How hard will it be to remake all of that kind of stuff? Those are the questions that you need to handle. And sometimes the answer is that you need to make the simplest system that just does what you need right now, because then the surface area is low. And if you need to replace chunks of it, you have very little stuff to replace. Whereas if you build this big system that has like generic features and all this kind of fancy shit that can potentially plug in stuff here and there and like all this kind of cool shit, trying to replace that or refactor that or whatever is going to be a nightmare. And generally these days, having explicit behaviors, simple selection logic is the right approach, primarily because the way that the team compositions are has shifted drastically, that we have fundamentally more, or rather we have less technical teams. We have a lot more non-technical content creators building the data, right? A lot of the designers are not very technical. There's less programmers. A lot of companies are even like not hiring that many programmers, because they think that they can, for example, with tools like Unreal 5 or whatever, that fundamentally the designers can build the games themselves, through Blueprint or whatever else. And so the team, the technical knowledge, technical skill on a lot of areas has reduced, which is natural. That's what happens once, an industry evolves and grows and tools improve. That said, given that fact, so as a programmer, you need to now cater to that audience to a large degree and say, like, how can I enable them to do their best work, right? Is that by me giving them a black box planner? Probably not, right? But if I give them a very simple way to, create behaviors and then select from those behaviors based on some conditions, that's probably what they need and that's probably what they want and that's probably how they will be successful, right? So to a large degree, we need to change the way our mindset works and say, like, it needs to be less about me doing cool tech and more about solving the reality of the industry right now. Is maybe as not fun as it is, but that's what is the right thing to do, right? So coming on to behaviors, rant over. Behaviors are very simple. They are a sequence of actions that achieves a goal. That's it. You move to a position, you play an animation. You move to a position while shooting or reloading. You play a reaction and an audio bark. It's just fundamentally just a sequencer for the actuation layer. Behavior should have some degree of settings and configs that can control certain like aspects of it, right? For example, a ranged attack behavior might want to say, hey, you need to be doing this behavior with a very aggressive firing rate. So prefer full automatic versus like burst fire or something, because you might want to reuse that same behavior in a different context within the same AI, but there you wanted to have it more of the aimed fire. So you want to say, hey, I need you to do range combat, but prefer aim versus, less aggressive, more, aimed. Or you might want to say, hey, I have a melee attack behavior and the settings are which attack, at which distance can I trigger the attack, and some other settings that maybe a designer wants to reuse. And then they can put that melee attack behavior in like 10 places with slightly different tweaks, and have a lot of variety in the AI without you having to necessarily write new logic for their behavior or whatever else is there. There's multiple solutions for authoring these behaviors. We did them primarily in pure code because they were relatively simple and they were fast to write. And they didn't really change much. Designer had a very clear idea of what they needed. We did the code within like a day, gave them a first version with some settings, and did a couple of back and forths on it, and that was it. It wasn't something that had a lot of churn or dev on it. So us trying to build data-driven authoring tools for that would have been a waste of time, and the designers really didn't care. They just said, I need to run to a point and punch the dude. And it's like, cool, we'll give you a thing. We'll give you some distances for when to trigger the attack animation. We'll give you a thing to specify what it's attack animation. We'll give you a thing to potentially control how fast they get there or whatever else. And that was all they needed. Again, I'm going to sound like a broken record, but try to keep the behavior separate from the selection mechanism. The idea being here is that you should be able to, again, test the behavior via a test harness. I should be able to say, hey, I want to trigger a melee attack behavior and test out that behavior. The goal knowledge entries that I mentioned earlier kind of simplify this because fundamentally they act as the primary preconditions for these behaviors. So for example, you'll have a combat goal that gives you like the enemies, a cover goal that gives you the covers. And based on that, you can test out a behavior by just setting the appropriate information in the goals and saying run behavior. Right, you need to do a bunch of work to build a test harness that can handle a lot of this stuff, but there are some benefits in doing this. Again, certain things about data access. Behaviors should basically just have read-only knowledge to the read-only access to the knowledge, as well as the world state. Again, primarily because you should be able to parallelize behaviors. There's no reason not to, right? The actions we talked about, they can maybe stay on the main thread, but there's no reason to not parallelize this. The only place where they might have read access to knowledge is for the goal entries, just to mark them as, hey, completed or potentially failed. Because behaviors, again, they should support failures. A behavior can fail, right? You might try an attack, and midway through the attack, the character moves out of the way and you miss the attack, or something happens, the nav mesh changes under your feet, and now the attack can't complete or whatever else. So you need to be able to support that failure. And again, once you can support failure, it simplifies debugging and logging, because when you fail, you write down why you fail, you log it somewhere, you track it. It's a lot easier to figure out when you get a QA report saying, hey, AI are whiffing all their attacks, and then you look at the log and it's telling you that there's something wrong with the nav mesh. You know, it's a much simpler way to debug than it's, you know, silently completing, and then now you have to go step through the code and figure out what the hell's going on. So when we talk about like behavior selection, there's a million ways to do this. Depends what you need and stuff. So I don't have the time. This is already getting to be a very long thing. So what I'm going to just cover quickly is the things that you need in your behavior selection system. And then you can kind of on your own kind of go back and look into how would I solve this problem given that these constraints that I have. So imagine I have a set of behaviors that an AI has. How do I pick what's appropriate? Well, the basic requirements for a behavior selection system, no matter what the case is, I'm assuming that the condition stuff you've already handled and the precondition stuff, is one, being able to sequence multiple behaviors. So having a combo system is a very common thing, especially in melee games. You might want to have a mechanism that says, hey, if I do melee attack 1, I want to follow it up with melee attack, you know, another melee attack, and then I want to do a finisher. You know, that's sort of maybe a combo system that I want to build in there that allows me to do that. But then if I, you know, break out of it, I leave and, you know, pick a different behavior. You want to have cooldowns supported at, you know, native level, because that is a very common thing a designer might want to do, saying like, hey, I did this behavior, I don't want to do this behavior again within the next 5 seconds. Super common thing. Your behavior selection system should handle this in a simple way, not in the way that certain things like behavior trees handle it, which anyways, you want to be able to support preconditions, you know, like custom ones in very unique scenarios. You want the behavior to have preconditions, but you also want to be able to add additional ones that could be based on situation, based on, you know, certain specifications. And you also want to be able to reuse the same behavior in multiple places with different settings. And that should be an easy thing to use, not them having to create multiple configs and linking shit to whatever. They want to just basically say, hey, I want to click this behavior in this scenario and switch the settings to whatever I need in that case. Then when it comes to more advanced requirements, there's 2 things that are extremely useful that very few systems can actually do. The one is to be able to disable existing behavior options for an archetype. So I spawn an AI, it might have a heavy attack, but in a very specific situation, again, imagine level 5, encounter 3, whatever, they're mind controlled and now they don't have a heavy attack, and instead they do a new special case area of effect attack. So I need to be able to disable the heavy attack, and I want to inject a new behavior into that archetype. without redoing the archetype, without duplicating and deriving and inserting. I want to be able to, at runtime, take any archetype, spawn them in, say, I want your heavy attack disabled, and I want you to do this other attack instead, right? Because it's a special case thing. And potentially, if you're doing something that's more systemic, you don't even know what archetype is going to spawn in, right? It might have been faction A in one case, and if you're a higher level, it might have been faction B, or maybe, you know, depending on what you did in the game before that, it might have been both A and B, and now you need to inject and disable stuff on both. That should be something that the system supports. Very few do that because of inherent problems with the approach. Now, what options do you have for behavior selection? Well, I touched them before. For example, you have state machines, you have decision trees, behavior trees, potentially utility systems. Every single one of these has pros and cons, right? They're good at some things, bad at other things, easy to use in one case, horrific to use in another case. This is my troll face one where personally I wouldn't use any of these. What I'm going to do at some point is I'm going to do a follow-up with how I think behavior selection should be done. That basically covers all of the use cases. I don't want to do it now because it's going to be an information overload. And if I do a follow-up, it's something that can be more kind of tailored for it and simpler to understand. That being said, I think it's still worth going through all of those options, because what I've done in my case is taken the best bits of each one to some degree and smushed it together and simplified it. But it's worth understanding each one of those approaches because they have benefits not just in AI, in other areas too, right? It's good to understand state machines and hierarchical state machines. It's good to understand what a decision tree is versus a behavior tree. All right, I think I just dropped out there for a bit. Hopefully it's still working. Anyways, so long story short, worth reading up on all of these. Be very careful with each one. I'm going to mention behavior trees explicitly right now, primarily because they are still extremely popular for some reason. And I'm not entirely sure why. I would have thought by now people have been aware of all the problems and dealt with all the issues and stuff. I've covered some of the problems. There's a YouTube link about the AI Arborist talk. There's an article I also wrote about things. And funnily enough, I had a conversation at lunch with a friend that's now looking into building a new AI system in a company. And he was like, oh, I think we'll just use behavior trees. And I was like, no, you know, and then like we talked for a while and he was like, oh yeah, shit, that those could be actually potential problems. So I'm going to look into it. I definitely would not recommend that you build your decision-making using a behavior tree. If you want to do your behaviors, like the actual like sequencing of actions and stuff with a behavior tree, by all means, I think they're good for that. You know, I'm not going to tell you not to do that, but your actual selection mechanism, I would absolutely not suggest you do behavior trees. Probably you're better off just starting with a state machine and then figuring out from there, you know. So the last thing I want to cover today is sort of those management paradigms that I mentioned before, which was the agent-centric versus the manager approach. Fundamentally in games, we have more than one agent at a time. That's just the reality. And these agents need to either cooperate or coordinate together. And when I say coordinate, it means like also when they're fighting with each other, they need to coordinate those attacks and those kind of things. Now, there are two primary management paradigms for how to build your AI. The first one, and one of the more common ones, is manager-centric. Basically, what this means is there is a manager that controls all of the agents and basically tells them what to do. Another term for this is director coordinator. Lots of places have their own names for this. Fundamentally, AI have no agency. They are told what to do and they do what they're told. The other approach is agent-centric. This is a different way in that agents will take independent actions based on what they know about the environment, right? There's nobody else telling them what to do. They are making their own decisions. Those are the two primary options. Now, what ends up happening is, in almost every scenario that I've seen, these two get smushed together and you have this giant clusterfuck of some things are manager-based, some things are agent-centric, there's conflicting orders coming in, there's prioritization issues, there's a whole bunch of things. If you're building an AI system, pick one of these two and just stick to it. If you want to do manager, then you have managers and you just use managers. If you want to go agent-centric, then you just stick to agent-centric. Now, let's talk about the manager approach. Fundamentally, the manager approach assumes that your agents are puppets. It is an external replacement for the decision-making. Agents do not have a brain. They do not have anything. They have an action layer and a knowledge. And the knowledge is primarily used by the manager to write data in and out that it needs, right? But there is no brain on the AI. If the manager is removed, you'll just have a bunch of characters standing, idling, doing nothing. Agents do not have any decision-making control. Everything is forced. This approach is probably more useful for games that have like lots and lots of dumb agents. So if you're doing a zombie game or some kind of horde mode or whatever else, this is probably a good option for this because your agents are primarily just charging at the player to die, right? You don't need a lot of control. There's not a lot of like interaction between them, special case scenarios, whatever else. There is another misconception to a large degree with the manager systems is that a lot of people think when it comes to group behaviors, this is the only way to do them. And it really, really isn't. But a lot of people are convinced that if they want coordination and they want group behaviors, they need a manager for this. So I'll go through a few examples of how the managers primarily work. So basic scenario, we've got 3 agents chilling. One of them's patrolling, one of them's just wandering around, and another's just standing idle. And we have an idle manager. That idle manager is just basically switching their behaviors from wander, patrol, idle, whatever. All of a sudden, the player jumps in. Boom. Now we need to react to the player. It is not the idle manager's responsibility to do that because it is just managing the idle situation. So now you need an additional system on top of that, sort of like an AI director or a global manager that is looking at the whole game as a whole and saying, what should I be doing? When should I transition characters from one manager to another? So what happens is we have the AI director coming in and says, hey, there's a player near an AI. That AI with its visual sensors or whatever detects the player. I need to trigger combat because, fight time. So what ends up happening is that we basically take that first character, that first agent, we shove it into a combat manager, and the combat manager says, okay, you're just joining. So the first thing you need to do is you need to play a reaction to the player because, we've just created a combat manager. You're the first entry. So boom, reaction time. At this point, the other two may have now noticed that, hey, an allied agent is in combat, or they can see the player or something. They need to now join. So they basically, the global manager is like, okay, I need to add these 2 agents to the combat system. So while that's happening, the other agent's done with its reaction and decides, okay, it doesn't decide. The combat manager says, well, you're done with your reaction. You need to attack. Then the other 2 are joining this combat manager. We don't need the idle manager anymore. It's removed. And now the combat manager says, well, I've got one character attacking. So the other 2, I think it's best for them to position it as, to circle the player or whatever, and that they will start moving. And that's kind of the methodology, the paradigm of the manager. You have one system that's got a top-down view of the scenario, and it's just issuing orders for each of the agents as a group. You also have 2 ways of managing this stuff. You could have a single manager, which is basically managing the whole world. So you have one idle manager, and every agent in idle is inside that manager, and that manager is then figuring out what to do where, how. The other option is that you dynamically create managers as needed, and they're usually tied to spatial locations or groups of agents, that sort of thing. So you might have 2 distinct group of agents in different parts of the level, and you might have 2 managers controlling this. This is another relatively common approach But this thing kind of brings in a bunch of other issues in terms of like, when do I transition between, managers? How do I merge managers? Blah, blah, blah. When we talk about agent-centric, as I mentioned, it's basically the agent making its own decision. They are still the global information systems. They are not managers. They are just information. So a lot of times people will, as I said, they mix the two concepts. So for example, they may be tempted to have the global information systems strongly suggest things for the agent to do. And at that point, the line between manager and data store blurs. And then you start to kind of shift responsibility into those systems versus the agent itself. Need to be careful with this one. And again, agent-centric is not very common. And in fact, to be honest, I've never really seen it except for places where I've been like pushing for it, primarily because there is this misconception that you cannot do group behaviors with it, because each agent has to make up its own mind. It doesn't have shared information. If I want them to move in a specific group and I want them to have a specific lockstep thing, you can't do that because you need to have shared information. That's kind of strange because, as I mentioned at the start of the thing, my background was primarily in like traditional AI. And when I was in university, we used to have a, this will age me pretty badly, but we had a robot soccer team where we basically used to compete against other universities, where we would have, I think it was 4 robots playing against 4 other robots, and trying to score like in a soccer game with a webcam looking down and then moving. But each of those robots wasn't linked to any other because, back then there wasn't really Wi-Fi and stuff. And they were making decisions individualistically, but still trying to work together as a team by passing the ball to each other and trying to score and whatever. And so for me, when I started in games, I was immediately told it's impossible to do group behaviors agent-centric. And I was like, but that's exactly what we did with these soccer robots, and that's kind of a very interesting approach where I've been to UB and I've been to a bunch of companies and I always get told the same thing. It's like, well, if I have group behaviors, I need a manager. The other cool thing about the agent-centric is because it's agent-centric, you will get a lot of the time more understandable and sometimes emergent behaviors where the AI will react how you would expect, because it is making its decision. Like you throw a wrench to make a noise and you'll have all the agents that hear it react to it. Whereas sometimes with the manager approach, the game design rule being like, well, I want one character to react, and it will pick the closest character and it will react. So if you throw the wrench a little bit to the left, a little bit to the right, you might get different characters reacting. And that can look janky or broken, or the player might not understand what's going on. Again, that's more of a design flaw, but it's very easy to implement that within the manager approach because people are thinking as top down again, and they're saying, well, I only want one character to react, so pick the closest. And it's like, okay, but there's so many edge cases. Whereas with the agent-centric, it's like each one will react. Maybe one will investigate and the others won't, but they'll all react. They'll all kind of play a bark or whatever. And then you have another system that says, if 3 agents request a bark, don't play 3 barks. Play the one closest to the player or whatever else. You have ways to manage the side effects of all 3 reacting. So it's a bit of a mindset shift there you have to take into account. So with an example of that combat scenario, we have the same setup, except now there's no manager involved. Each agent is picking what it wants to do. The player jumps in. One of them turns to a reaction, and the other one decides, well, I can see there's an enemy. I can already see a player's reacting, so I decide the combat move is the best thing for me right now. The other one decides to also do a combat move too, and the first one decides, okay, I've played my reaction, so I should do an attack. Or all 3 could have reacted. It's entirely up to like how you want to do that, because, for example, the other 2 agents could have had a view in the first play and they say, I see a character in a reaction. There's no point me playing a reaction, so I'm going to join the fight. Yes, there's a comment for information sharing. You could have a type of stim. I would think yep, that's exactly how you would do that. And I'm going to cover that exact approach in a few slides. So, yep, valid. So there's also a hybrid, which is what I mentioned, that it is literally the worst approach, because what ends up happening is agents start out agent-centric when they're relaxed and idle. Then control is transitioned to a manager for a given situation. So you'll take an agent and then you'll say, okay, now you're under the control of the combat system. Oh, you've lost the play. You can't see more, so combat's over. Now you're under the control of the search system. Oh shit, combat started again. We're going to move you back to the combat system. You know, and that kind of leaves the agent in a weird state where it's making some decision making on its own side, but it's also having behaviors forced on it by a manager. So now it has a brain, but there's also a manager running that is telling it, you need to go here, you need to do this, you need to play this behavior. And the brain now needs to match what the manager is telling it. And that's where you can get a lot of problems when you have a disagreement about what the agent should actually be doing, right? So the biggest one is sometimes the decision making says, you know what, I'm doing something more important than what the manager's telling me. So fuck what the manager's doing. I'm going to do my behavior. And at that point, the manager thinks it's doing X, the agent's doing Y, and there's a miscommunication and potentially things go horribly, horribly wrong. So now the manager has to handle the case where the agent doesn't do what it's supposed to and try to recover from that, or basically it will override whatever the agent's doing. So you might get really weird things like mid-reaction, the agent just flips into a punch or something. It doesn't finish the reaction. You can get into a lot of trouble there, and it's a lot of kind of like, you know, chasing bugs and issues and stuff and tweaking this and poking that, and you pull here and a lever goes up here, you pull that lever, thing pops up here. There's a bunch of chasing your tail. Another big headache is the transfer between managers, especially if you're trying to do multiplayer and you have multiple combat managers within a close area, because you may have overlapping not overlapping, but close enough that they don't initially overlap. But as the players move together, they kite the enemies, and all of a sudden now you have two overlapping managers, and now you have to merge them together and not fuck up everything in either one or the prior knowledge or whatever else. This is primarily if you have a multiple manager system, which in a multiplayer game is probably a better thing because they can manage timers, cooldowns, whatever separately, which is kind of what you want to handle two players that might be very separate from one another. But then when you merge them, you need to deal with all of that mess. And what if now two AI were in a behavior that was only allowed to have one off? So how do you handle that? You know, there's a bunch of stuff to think of there. And also when agents usually join a new manager, that's when the reactions are triggered. So for example, if I go from idle to a combat manager, me entering the combat manager is where I will be told, hey, you're entering combat, so you need to play your transition or your reaction to be in combat. Or hey, you're entering a alert or an investigation manager, so now you need to play the alerting based on what pulled you into this manager. Was it a stim? Was it whatever? So that has to be handled explicitly in each of those managers. And you know, it has to be handled in the managers, but it also has to be handled in the behaviors. And sometimes it's done only in the behaviors where the manager is setting a flag to tell the thing to do a reaction because it can't rely on the knowledge, because it needs to control when they happen. And you end up with this giant mess of like half of it's in one place, half of it's in the other, and they're all linked together with a bunch of flags. And then when you need to put in hacks, it propagates across all systems. So at one point, you lose sight of what happens when I do a specific thing. If I remove a hack here, is it going to break something else? Because you don't know, because everything's now interlinked. Now, the question is, there's a lot of headaches and a lot of issues and a lot of stuff. So why is this so popular? Well, I think fundamentally is because certain things are easier in the agent-centric, like the relaxed state is generally easier. Patrol, when I'm done, wander, idle, whatever. Reaction's a lot easier to do. You just put a bunch of reaction behaviors and schedule, you know, prioritize them, whatever. It generally is a little bit easier, a little bit simpler for those cases, but I don't think that's a really strong argument as to why this is chosen. Another option is that the idea is that group behavior coordination requires a manager. I think this is one that's a little bit stronger, but it doesn't necessarily say why did we did a hybrid. And my gut feeling is that it's like an instinct or how it's always been done, right? Because naively people will be like, well, it's an agent, so they need a brain. So I'll add a brain, and then that brain will need a decision, behavior tree or a blah, 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 whatever. So I'll start doing a planner or a behavior tree system for the agent, and we're going to do that. It's going to be cool. Oh shit, now we need group behaviors, so now we need managers. Boom, we add a manager, and now we're fucked, right? Because now we've got the split responsibility, right? So I think people just need to stop and think and say, what are we trying to make? And pick one of these paradigms and just stick to it. Realistically, you can do both. You can do everything in either one. It is just in some cases one will be more will be simpler versus the other, depending what you want to do. And in some cases, one will have different performance characteristics than the other. If I'm doing a horde mode, having a manager where I update all the positions and movement of all characters in one shot will be better than if I did an agent-centric approach with like 10,000 characters. Right? Again, it depends what your needs are, depends what you think the game is going to be, and make the right choices. You can even have both. You can have part of your agents use manager, for example, zombies in a horde mode. You can have another part of them using an agent-centric approach that are more kind of smarter with a lot more abilities and a lot of kind of stuff. Try to figure out the right approach, but just do not mix these two together. Nothing good can ever come out of it. It's like, just don't. So the last thing we're going to cover is the group behavior aspect. So there are multiple ways to do this. Honestly, I would actually argue that doing it agent-centric kind of scales a little bit better because you don't have a manager that has to manage different archetypes and stuff. It's kind of forcing you to build things in a way that is more generic and more kind of modular so that it can potentially scale better because you don't have the direct access to all the different other agents and all the different other archetypes. And you can't easily go, well, if I have a heavy and I have a light character and I have this character, then trigger this behavior on each one, right? You have to do things in a different way. And once you go down that path, you'll notice that things will scale better. And if you want to add functionality to a different agent, to a different archetype, you probably already have the tools available to do that quickly and easily because you've had to do it already just as the default version. Additionally, a lot of the stuff here for scaling applies to manager approaches because you can build it in the exact same way with the manager system. You don't have to go down the route of explicitly saying, what archetypes do I have and how do I combine them together? That is a very naive way that doesn't scale. And unfortunately, it's one that I've seen a lot where you have code like if civilian, if guard, if police, if blood, and combine this, and generally not a good solution. Another question with the group behavior stuff is, remember the whole dev view versus player view? I would ask primarily, why do you need a group behavior? What is it solving? Is it going to even be noticeable by the player, right? And a lot of cases, can I fake it in a way that it isn't, that the player thinks there's a group behavior going on, but there really isn't, right? And in a lot of cases, you can fake that with just some shared knowledge, some shared information, voice prompts, like it was mentioned in the thing, like yelling out something. A lot of why everybody thinks fear is so intelligent was because of the bark system. I don't necessarily think the AI at the time was doing anything incredibly smart, but they were doing interesting barks, and the player was making the story in their head that, oh man, the AI said this thing and then I didn't see it for a while, so it must have obviously flanked me. And there's a whole level of storytelling going on inside the player's head that might not match reality. And that's the important thing, is to kind of put yourself in the shoes of the player and say, like, forget that you know how everything works behind the scenes. What does it feel like when you play it? So here's a very basic example. Like, I have an agent that basically wants to go to that empty cover, and we want to make them seem smart. So we want to have some sort of like covering fire and everything else. So we want to make it look like this coordination and group behavior and stuff. So what it can do is it can issue a bark and saying, hey, cover me. Yells out, cover me. We can then spawn a stim volume that basically says, hey, I need covering fire. Simply, we just make a volume. It would yell cover me if it knows that there's other agents around it. So there is some prior knowledge that it checks its knowledge and says, hey, I have other agents I want to do a move to. Because I have other agents, And I think I have a cooldown available, so I'm just going to say cover me and see what happens. So it yells cover me. It's going to move no matter what. Whether it gets covered or not doesn't matter. It's going to move. It's just said, I've issued the spark, I've created the stim zone. The other agent now finds itself inside the stim zone and it's in cover. And potentially what it's going to do is it's going to say, well, now is a good time for me to get up out of cover and shoot, right? Maybe the stim zone will influence that timer a little bit more. You can set up some stuff that, you know, in your precondition, it says, you know, when I'm with the stim zone, prefer this behavior over another. So when it gets up to shoot, it's the regular stand up and shoot from cover. It can yell a bark saying covering, you know, and then you have the other character move while the other one's shooting, right? There's no coordination there. There's no group behavior. There's nothing. But what the player is going to see is it's going to see one agent saying cover me, and another agent at some point is going to get up and start shooting, you know, and potentially play a bark that says, got you covered or something. And the other one's going to run at some point. Maybe the timing is going to be a little bit bad where the one starts running before the other's gotten up and started shooting. I don't think it necessarily is going to matter. Or I don't think if that happens that the player's going to be like, oh my God, the timing's off, 0 out of 10, bad game, what the fuck? Lazy devs, you know? Another option could be is that we have the exact same situation, but the other agent is already firing. So you could have it yell to cover me. It's already in the cover behavior. If it detects that it's in the zone while it's already shooting, it can just issue the bark and just say covering, and we'd have the exact same happen again. And, you know, we faked to a large degree group behavior. Didn't need any coordination, didn't need any managers, didn't need anything crazy like that. Another option would be, for example, you have a vehicle and you want to have, you know, your agents use it as a cover so that they go behind the vehicle and they move with it. An easy approach to that would be as you have the vehicle at some point drive up, and now you need the agents to sort of follow it and stuff. And how to do that? Well, a simple approach would be is you can create smart objects or interactable objects that get dragged behind the vehicle that says, hey, these are cover points or mobile cover points or whatever else. And an agent can decide, hey, I see a mobile cover point. I think it's a good thing to use that mobile cover point, so I'm going to go and attach to it. And as that mobile cover point moves, well, the agent will follow because it's already in a behavior that's saying, I'm in a mobile cover. You know, and as the cover moves, my behavior is telling me to follow the cover point as it moves. And now once I have that system built, I can attach it to a car. I could attach it to a tank. I can potentially attach it to another character and have like a character with a riot shield that has a cover point behind him. And now you have, you know, characters lining up and going single file down a corridor without any managers, without any kind of systems. And again, it's up to the designer to balance when it prefers to use a mobile cover versus when it prefers to stay in cover, a lot of those kind of things. Another approach would be to do something like social interactions, where we might have, for example, a fireplace that has 2 slots for smart object usage. One character can go and use the smart object, and the smart object tells it, hey, you're using a smart object. What you should be doing is warming your hands. And so it plays an animation that warms its hands, maybe says some dialogue, whatever, it doesn't matter. And at that point, another agent joins that interaction. Once the second agent joins, the smart object itself, as part of its smartness, it can basically say, well, I have 2 users now, so I can switch the behaviors of both. And instead of one of them warming the hands, the other standing idle, I can basically trigger a synchronized animation on both with some dialogues and a conversation playing. And internally in the smart object, you can manage what lines were said, what happens if there's an interruption, you go resume it, whatever happens. Again, there's no manager. Yes, the smart object is managing some of the coordination and synchronization, but none of the AI needs to know that there's a manager or anything going on. All they need to know is, I decided to use a smart object. What it tells me to do, it's irrelevant, you know? And you can fake a lot of stuff in the levels where people think that there's something smart going on, and it's just as simple as saying, if I have 1 agent, do this. If I have 2, then do this. So I think the major takeaway fundamentally is that a lot of the coordination cooperation that people ask for via group behaviors can actually be faked in a lot of ways without the need for explicit managers and group behaviors and code that says, oh, I have 2 characters, then they need to do this. If I have 3, then it's this formation. If it's 4, then it's another formation. And oh, if one dies, then this one has to be the leader, and then that has to. You don't need any of that shit, right? A lot of that is just complexity, and most of the time players aren't even going to notice. They're going to notice when something goes wrong with that system and there's a bug, but all the cool shit that you put in, I don't know how many of them will actually notice, because fundamentally, most of the YouTube videos and the comments will be about when the thing breaks, not when it's working well. So rather just try to keep things as simple as you can. The other thing is try to leverage smart objects or interactables as much as possible, because they can simplify a lot of things and they can fake a lot of stuff. They can really make things look smarter than they actually are, just purely with some very simple multi-state smart objects or smart objects that are moving around and dragging agents with them and that kind of thing. So if you can, definitely try to leverage those systems. So we're kind of wrapping this up right now, but there's so much information on a lot of this stuff that I could probably spend hours on any one of these topics. Based on what people want, let me know on Twitter and I can focus in deeply. I'm going to probably do one on my preferred way to do decision making, because I think that's kind of probably beneficial and the biggest thing lacking from this whole thing. And then past that point, we can talk about how to build smart object systems or how to solve certain navigation locomotion headaches like navlinks or exotic navigation, combat approaches, coordination, those sort of things, stealth loops. Depends what people are interested in, and I can, try to prepare something and do something on that. Apart from that, if there's any real questions or whatever else, I am generally pretty responsive on Twitter. So poke me and I'll try to get back to you as soon as I can. And yeah, thanks for joining me. Thank you for your time and enjoy the rest of your weekends. Cheers.